the title, linear functions, lines, slope, rate of change, very dramatic there, and models. Now, models, of course, again, a little mathematical fancy phrase they like to use for word problems, some word problems today. We're used to word problems. But again, linear functions. They're going to be lines. What's this wild about a line? I don't know, slope-intercept form we might see today. I might have to calculate the slope. I might have to figure out the y-intercept. They might ask me a question about what the slope represents. But slope, y-intercepts, we got it. Nothing too crazy. So slope, rate of change, models, yeah, that's what we're doing. Let's get into it. Now, this is just, why does math have to make things so tough? Linear function is in this form. And I'm like, really? Really? Notice they just got fancy and changed up M to A. Why? Just to make your life difficult. Of course, we know the number in front, we're used to it as M. We know the number in front of X, of course, is our slope. Why they changed to A, just to make your life difficult. And of course, the y-intercept is B. And again, to be a line, the other key thing about our functions, your highest exponent on the variable is a 1. Because if you go to a 2, now you're parabola, you're quadratic. 3, the cubic, 4, quartic, so on and so forth. So we are just looking at linear lines today. We know all sorts of good stuff about lines. Okay, determine whether the given function is linear. If it is linear, express it in the form ax plus b. So slope-intercept form. So I'm looking at the first one, and I was like, well, yeah, that's a line. Highest exponent, got it. The only thing I would say I don't like, of course, is the order. We should have the variable term first, so I'm just going to switch it up, meaning I'm going to put the 3x first, and then the 2. And of course, y-intercept 3, or sorry, slope 3, y-intercept 2, if they asked us. Now, looking at g, I can tell you right now, g is also, yes, a line, because you really have x to the first. But if I'm going to write it ax plus b, mx plus b, we should distribute and simplify. So let's run the 3 through, 3 times 1, 3 times negative 2x. And then, of course, I don't like the order. I'm just going to flip them around. Got it. Okay, C. First glance, I'm thinking, yes, C. But then I'm like, no. If you distribute x through, now you have I know I skipped the 4, but I was looking at this. I was like, oh, man. Now I got 3x squared. It's quadratic. It's a parabola. It's clearly not a line. I'm just going to put a big fat no on that. Got it. And you know I love a fraction, so I had to throw a fraction at you. So at first, next minute, like, fraction, I don't know. But again, exponent on the variable is a 1. That's a very dramatic one there. So it is a line. I need to get it in, it's painful to say ax plus b, mx plus b style. So first thing, I'm going to put the variable first. So I'm going to put the negative 5x first. Notice it's all over 4. So I'm going to split it up. Negative 5x over 4, and then plus 1 over 4. So now I know my slope, my y-intercept. I've got it in the right form. There we go. So nothing too dramatic there. Just be careful on your exponents. 1 as high as you can go on x. Okay. Oh gosh, I really should just write my own book sometimes. Let f be a linear function defined by that equation. Make a table of values weak to sketch it. I would never bother making a table of values to sketch it because I'm like, well, b. I'm just going to mark it out off of that, okay? Y-intercept 2, slope 3, up 3 over 1. If you want to make a table, I will show you. I can't draw very straight, so I put a lot of points on. Oh man, that got away from me. Pretend that's straight. Now, if you like the table of values, your table of values, pick any numbers you want, plug them in. 3 times 0, 0, plus 2. 3 times 1, 3. 3 times 2, 6, plus 2. Plot it, draw it. I personally find that obnoxious. All right, easy question. I love B. What's the slope of the graph? 3. That was hardly worth writing. Okay, got it. So any questions on drawing lines? I don't think we probably need to cover that anymore. All right, next up. Slope. We've done slope a million times. and rate of change. That's what we practiced yesterday. Now remember, slope and rate of change, really the same thing. It's just a wording, how you represent it. So for the linear function, of course, the slope of the graph and the rate of change are both equal to a. Your coefficient on x. We know that the number in front of x is the slope, and now we call it the rate of change. Now, this is an exciting question. Flip it over. What is the difference then between slope and rate of change? Well, none. There's no difference. No difference at all, kids. It's just how they word it. Difference in a point of view. Describing how a reservoir fills up over time, they're probably going to word that as rate of change. If you talk about how steep a staircase is, you're looking at slope, or maybe the grade of a hill that you're driving down, slope. It just depends on how they're going to phrase it, but they mean the same thing. So a dam is built on a river to create a reservoir. The water level in the reservoir at time t is given by that exciting equation. What is the slope of the graph? Well, okay, it's 4.5, the number in front of, they're using t this time instead of x. Okay, that's exciting. Now, at what rate is the water level in the reservoir changing? 4.5, okay? Your slope is how much it's changing, but because they're using like rate, I'm gonna fancy it up and kind of put a little label in here. So we're doing this, it's in feet, of course, and the time is given. So I'm gonna say 4.5 feet. I'm gonna throw a label on it, feet, of course, and we're doing our time. Did they give us a time? Time is given. I'm gonna assume the reservoir changing. They didn't give us the time, so I'm assuming t is 1. So I'm going to put per year. That's a very sloppy p. They didn't really give us a specific time. We're going to assume it's 1. So they're the same thing. It's just how they phrase it. Well, so a good review of rate of change, I guess. Making and using linear models. Oh, look at that. Or a reservoir we're filling in a pool. Okay. Water is being pumped into a swimming pool at the rate of 5 gallons per minute. Initially, the pool contains 200 gallons of water. Find a linear function v that models the volume of the water in the pool at any time t. Now, the key is we got to read this and we have to figure out what is our rate of change. How much is the pool filling over an amount of time? So it's going up by 5 gallons for every 1 minute. So there's my slope, aka my rate of change. And they want me to use the variable t, time. Now we need the y-intercept. Maybe look at the little picture over there. Y-intercept, your starting amount. When time is 0, there's 200 gallons in the pool. They started with 200. So that is your y-intercept. All right, B. If the pool has a capacity of 600 gallons, how long does it take to completely fill the pool? So how long? They want you to figure out what the time is, and you have 600 gallon capacity. So that's your volume. How much is in the pool? And we're just going to go through and do a little algebra here and solve for t. Not that exciting. Subtract 200. And of course, divide off by 5. And I'm going to label it. Make it look nice. 80. Now remember, time. So I'm just rereading my problem to see how are they measuring in time. Is it in seconds, minutes, hours, years? I don't know. Read it. Or in minutes. So 80 minutes. It's going to take it 80 minutes to fill up the pool to get it to 600 gallons. Really exciting stuff here today. Any questions on that guy? I like these linear functions. They're pretty easy stuff. All right, staircase. So staircase, of course, right away, I haven't even read it, but I'm thinking, ooh, staircase, slope. Probably going to use the word slope more so than maybe rate of change, but we know they're the same. Okay, in the figure, a staircase has been placed in a coordinate plane with the origin at the bottom left corner. You're like Vanna White, there it is. The red line, mine's red, yours is not. In the figure is the edge of the trim of the board of the staircase. A, find a linear function that models the height of the trim board above the floor. So, linear function. lines. We know how to write equations of lines. And look at, you have 2 points on your line. So I'm just going to jot down these coordinates, 12, 16, and my other one there, 36, 32. This is no different if I said, hey, here's these 2 points, make me an equation of the line. First I need the slope, so I got to do a little y2 minus y1 over x2 minus x1, and then we'll see where we're at from there. So I'm going to do my slope, y2 minus y1, x2 minus x1. All right, so 32 minus 16, of course, we've got 16. 36 minus 12. And of course, I'm going to reduce that. 8 goes into both of those. So 2/3. You might be like, man, she didn't leave us very much room to write this equation of line. Well, we really don't need any more work because you can look at this graph and get the y-intercept off of it. So I'm ready to write my equation. And they want me to use h. So my slope on that guy times x. Now, y-intercept, where it hits the y-axis, ding, 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 ding. Right there, I don't have to find it. I'm just going to say plus 8. Got it. All right, so I do the slope. That wasn't that big of a deal. If the space available to build the staircase is 11 feet wide, that's going to be a problem. How high does the staircase reach? Now, I say that's going to be a problem. I should have a T in there. We're in inches. My equation's in inches. They're giving us feet. So we got to do a little conversion. You're probably going to need your calculator for this. 11 feet equals how many? I'm going to leave some room there. Equals how many inches? How many inches in a foot? 12. So what's 11 times 12? Punch it in. 132, yeah. So just be careful. It doesn't happen very much on the homework, but just read closely. You might have to do a little conversion just for the record. Now, of course, that is, if we look, what we are putting in for x on that guy. Because if the space available is 11 feet wide, left to right, you're finding the height, y. So we are putting this in our equation over there for x. We want the height. So 2/3 times 132, because we had to convert, plus 8. And I punched that in earlier. I don't have it memorized. You get 96 inches for that. And if you wanted to convert it back to feet, because you started in feet, I mean, I guess you could. It would be 8 feet, but I'm just going to leave it. So yeah, so far we found slope and wrote an equation of line. I feel like I've taught you nothing new. So hey, let's continue on the trend and do some more slope and lines, right? John and Mary. I wish we had color copy machines so yours were in color. So John and Mary are driving westward along I-76 at constant speeds. The graphs in the figure show the distance, y in miles, that they have traveled from Philadelphia at time x in hours. So wordy. Where x equals 0 corresponds to noon. Note that at noon, John has already traveled 150 miles. Because John's the red one, so at noon times 0, he's up there at 150. Okay, that's exciting. At what speeds are John and Mary traveling? Who's traveling faster? How does this show up in the graph? Okay, so let's talk about all of this. Let's just start with John, I guess, first. I'm going to red, since my line for John's in red. So you can see there's the 2 points on there. So all I'm going to do is copy down those coordinates of the point and find the slope or the rate of change. Elliot.
Actually, in this graph, because both of the lines intersect exact coordinates of the graph, you can find the slope just by counting.
You can just count them, yes, for sure. So I'm looking at my coordinates. I'm at 2, 250, if you want to do your points. And then, of course, your other one, we're over here at 4, 350. So I don't care if you do your y2 minus y1, x2 minus x1, or if you do a little, like Elliot was telling us, Elliot was getting ahead of me. If you do your rise over your run, just be careful about your scaling, how they're scaling these. Of course, they're counting by 50s over there. Doesn't matter to me. Calculate your slope. What do you got for John? You can almost do it in your head because you got 100 over 2. What's 100 over 2? 50, yeah. And I'm going to label. I can't help myself. I like to label. So that's in miles per hour. And then you're going to do the slope. I'm going to do it in blue because Mary's line is in blue. Right. Good old Mary. So again, you can do it off the points. I'm going to jot them down. Or you can count your rise over the run. So the left point for Mary, she's at 2, 150. Or of course the right one, Mary's at 4, 300. Or you can count your rise over the run. It doesn't matter to me how you do it, just get your slope, aka your rate of change. So if you subtract them, we're going to have 150 over 2. What's 150 over 2? 75, I heard it. Miles per hour. Okay, real question is now, at what speeds are John and traveling? Okay, yeah, John's at 50. Man, John's slow. Mary's got the hammer down, 75. Who's traveling faster? Well, that's the obvious answer there. And how does it show up on the graph? We'll talk about that in a second. First question for you, who's traveling faster? Mary. Okay, Mary's faster. Mary is traveling faster. I would just circle Mary. I just feel like I should write out a sentence so it looks pretty. Okay, how does that show up on the graph? Like I could tell you before I even did any, let's erase all my markings on here. I can tell you just from looking at the lines, even if you didn't give me any numbers on the graph, you didn't even label the axes, I can tell you Mary's going faster. How? What's different about her line? It's more steep, it's steeper. So I can tell you she's going quicker, faster. I can tell you just from looking at the lines, I don't even need the numbers. Okay. All right, B, find functions that model the distances that John and Mary have traveled. Well, we kind of got some info to help us up here for that function. Now, we're just talking equations of lines. It pains me to keep saying AX plus B. We're used to our MX plus B. Well, we already have the slope, so we're going to be in good shape here. So equation they want for each of them. So John, all right, I'm on it. They want functions, so I'm going to write function notation instead of Y. We've got the slope 50 times X. Take a look at good old John, the red line. What's your Y-intercept for John? Where does it hit the Y-axis? 150. Okay, Mary, same thing. They want one for her. Oh, Mary, she's, man, hammered down with her 75 miles per hour. What is her Y-intercept? 0. So, I mean, for dramatic emphasis, so we talked about it, I'm going to put plus 0. But of course, I would not actually write that on a quiz or test or my homework. I would just do, okay, all right. I couldn't fit it all in one slide, so I got to click to the next one. How far will John and Mary have traveled at 5 p.m.? So I'm going to go back to my equations. We want to look at 5 p.m. Time is on X. So I don't know, let's put a 5 in for the X's and calculate them out. So in your calculator, let's do John first. I'm just going to do J for John. We're going to do 50 times 5 plus 150. All right, punch it in, do it in your head. I don't care. What's 50 times 5? 250 plus 150. 400, yep. So good old John went 400 miles. I'm just going to do M for Mary. So her function, remember, was 75x. Or in our case, we're putting 5 in. What's 75 times 5? Okay, got it. D, final question of the day. For what time period is Mary behind John? Will Mary overtake John? If so, at what time? Well, let's look at the graph here. Now, if you continue these lines, if we actually continued and extended our graph here, they are going to eventually meet here in the middle. They will equal each other out, and then we can kind of compare, key word I said there was equal each other out. We can kind of compare them after they equal each other out, what's happening. So I'm just gonna set, I'm not doing the 0 though, I'm gonna set these two expressions equal and see what time they first match up and equal each other. So first thing I'm gonna do is just 50x plus 150. When does that equal 75x? When does John equal out to Mary? Okay, go through and solve that. I'm not going to bore you. You can solve it. I know you can solve it. You get 6. So what does this mean? At 6 p.m., they're even. Okay? So if you look at the graph, what time period is Mary behind John? I'm going to go back to the picture. So Mary is behind John, clearly, okay, from 0 to 6. Because she's behind, so she's behind. Now, to just make this fancy, it's 0. Remember, x equals 0 corresponds to noon. So I'm going to say she's behind from noon to 6 p.m. A p.m. there. Okay. And then, of course, we already figured it out. At what time does Mary overtake him? At 6. Yeah, I heard it. So at what time? So I'm going to say she overtakes John at 6 p.m. I ran out of room. I put the p.m. underneath there. Okay. So you have to kind of, and like I did, just extend your graphs, and you can see Mary's overtaking him. John's going to fall behind if you continue on drawing those two lines out from one another. So I'm going to give you your 2-5 homework, remember. I'm going to give it to you.